Swayam Prabha. Digital India. Educated India.
Thank you for coming back to this series of lectures dealing with additive manufacturing of ceramics. So this morning we looked at different technologies. Before doing that, I mentioned some general things about additive manufacturing, that it makes sense for because it can provide specific advantages versus conventional manufacturing technologies. We also saw that it has some drawbacks. And then I talked about the different categories of additive manufacturing technologies that are being recognized by the international standard. And I didn't describe them in too much detail, but I tried to highlight their applicability to ceramic feedstocks, specifically or mainly considering using systems that are based on ceramic particles. We will then progress to the use of chemical approaches of making ceramics, which is my main specialty. And we will discuss if and what kind of advantages you might have if you go down that route. But we are still in the process of discussing the different types of technologies, specifically for making ceramic materials. And out of the 7 categories, I'm going to highlight or remind you the characteristics of 4 categories, which are the most used for making components out of ceramics. So VAT photopolymerization, and I remind you that this comprises SLA, so laser-based approaches, DLP, so it's different way of providing an energy light source to the photocurable feedstock, 2-photon polymerization and VAT photopolymerization. For material extrusion, we have fused filament fabrication, we have direct inviting, and we also have pellet extrusion. Material jetting is one of the minor possibilities for making ceramics using additive manufacturing, but it is still worth considering. And binder jetting is also an isolated approach that has some specific advantages and characteristics. So we can say that VAT photopolymerization gives you a very high resolution, and of course we need to specify that to quantify that. And when I talk about resolution, bear in mind that you have 3, of course, directions in space. The Z direction, the layer thickness can be down to, I don't know, a few microns, 10 microns, but typically you want to be working with 25 upwards, down up to 100 microns in order to not have to take too long to build your part. So the resolution there, it's in the XY plane. For volumetric additive manufacturing, you can have a better resolution in 3 dimensions. It allows you to obtain dense and fine microstructure, also for advanced ceramics. And you have a wide geometrical flexibility. One of the issues that I did not discuss this morning is that the difference between the various additive manufacturing technologies is not just in terms of the type of feedstock that you can use, the type of ceramic material that you can use, but it is also a difference based on the structures that you can build. There are certain characteristics for each technology. They make that technology suitable for building specific shapes. And I will be discussing that more later on. I'm highlighting the positive characteristics of each technology. So in terms of materials extrusion, the advantages are that you have a very flexible possibilities in terms of the choice of materials that you want to use. You can generate small components, but people are using extrusion-based technologies, for instance, in the construction business. So they can have nozzles that are a few centimeters in size, and you can build very large structures using this approach. It is potentially fast, but it depends also on the geometry and diameter of the nozzle. And again, with material extrusion, you can obtain dense and fine microstructure also for advanced ceramics. And this kind of answers one of the questions that we had this morning. Material jetting is good for multi-material parts. Actually, also material extrusion is good for multi-material parts. Material jetting has a better resolution with respect to material extrusion because typically they use smaller nozzle, and you have no problems in obtaining a dense ceramic. Binder jetting is very fast for medium and large areas, very flexible. And when I say fast for medium and large areas, I also mean that you can build a lot of different components of different shapes within that large area. And it is flexible and easy to use with new materials. In terms of issues, but photopolymerization has difficulties with the binding due to the large volume of organics and long time for thick parts. So you have a restricted wall thickness. Here is written 10 to 20 millimeters, but basically 10 millimeters is kind of the limit that you can reach. And sometimes you need support structures for building complex structures, but it depends on the rheology of the viscosity of the system. Material extrusion has a much more limited geometrical flexibilities. One of the features of material extrusion is that, especially for directing writing, you have either a syringe with gas or a syringe with a piston, and they're pushing on the content of the syringe and extruding them through a nozzle, or you have a corkscrew extruder that pushes the material. But in any way you do that, it is very difficult to precisely stop the flow. You can stop you can tell the printer to stop printing, but the material keeps flowing at least for a fraction of a second. So start and stop is very difficult. Fuse filament fabrication is much better from that point of view because of the fast cooling that you can achieve. You can actually do point-to-point printing with that technology. But for direct ink writing, which is used widely for additive manufacturing of ceramics, you have this problem, which means that when you print, you need to follow a continuous path. And this is not just an issue with the software, I mean, the program code that you need to input, but you need to, this means that if you conceive of a geometry, you also need to design a continuous path for the printing head that will lead you to that specific geometry that you have designed. And this, for certain geometries, is not possible. So this makes the material extrusion technologies less, more limited from the point of view of geometry. And then in terms of surface quality, again, since you are extruding through nozzles that have a minimum of 200 microns in size, if you have a highly filled filament, you typically cannot go below 300 microns, then the stair-stepping effect is much evident. Material jetting, you have problems with the clogging of the printer head, very slow for large parts, and often you need a support material. Binder jetting has a medium resolution, better than material extrusion, worse than but photopolymerization. But as I mentioned, you cannot produce a dense component for any type of ceramic, which limits the applicability of the system unless you want to follow some post-infiltration approaches which are cumbersome. So additional features of the different technologies. Here I included also a new technology, layer-wise slurry deposition. This was developed by Jens Günster at BAM, the Research Institute in Berlin, following a very clever idea. Technology has been commercialized now by Litos. They acquired the patent. But the basic idea is this. Instead of the problem with depositing a layer of powders is the fact that you need flowable powders. I mentioned that this morning. And this leads to using coarse powders, hence porous body after sintering. With this approach, layer-wise slurry deposition, you actually use an aqueous slurry, which is typically used for making any kind of ceramic part. So you can use fine particles. And since you have water, that helps with spreading the layer, okay? So you can have highly concentrated pastes or slurries, and you can spread them evenly. Then the issue becomes how you consolidate that. And he came up with this idea of using a laser to selectively dry, and you have also some organics in the system that bind the particles. So he uses laser to inscribe the liquid layer. And then once he has finished processing the part, he has a component that has been built using fine particles, and this can be sintered to full density. So this is another technology that has been added to this slide because this slide was kindly provided to me by a co-worker at BAM in Berlin. So coming back to this slide with the different additive manufacturing processes for ceramics, we can see that you have some characteristics for each technology in terms of the dimensions of the part that you can print, in terms of the wall thickness that you can process, in terms of the kind of microstructure, dense or porous that you get after sintering, what type of powder you can use, which is related to the type of microstructure that you obtain, and the surface quality. And of course, these are quite generic statements. But here you have a few comments that allow you to relate what fine, thick, small, large means quantitatively. And so nothing strange, but because nothing strange with respect to what I discussed this morning, but you can see that different technologies provide different characteristics to the final part. And then this means that when you have to decide what part you want to make, you should also decide what kind of technology you want to use for making that specific part. So the main message for my talk this morning that I'm finishing this afternoon is that ideally you should select the best technology for making that specific part with a specific geometry, with a specific type of material that you're interested in because of the properties that you will get. So this is quite a general statement. And when I told this to an audience where there were a lot of people from industry, afterwards they came to me and they told me, you're crazy, because we would never invest into a wide range of technologies because we would need trained people to look after the different technologies. And we want one technology that works for everything we do. I understand that point, but it is a pointless remark because they will not be able to obtain the best results if they use one single technology for making every type of part that they want to make. So this is quite important because the next step for this type of discussion would be to link artificial intelligence and modeling or predictive modeling optimization, not just to the shape that you're making, but also to the type of technology that you will use to make that specific part. So the main message today is that I would like to recognize that each technology has advantages and disadvantages, and you need to be aware of that. You shouldn't think that, okay, I want to make the shape, I can do it best with any type of technology, because that's not the case. So here are a list of potential applications. So case studies, we want to make an alumina component for the textile industry. Of course, alumina, high hardness, high wear resistance. So that's very good for fast-moving threads. We want to make, and for this, typically the dimension is small, wall thickness thin. We need very dense component. We can use very small. In order to do that, we need to use ceramic powder that has small size, and we need very good surface quality. Bioceramic for implants for biomedical applications. Again, the part doesn't need to be very large. Typically, it's a macroporous part, so the wall thickness is thin. We can accept, we want high porosity in the solid part. We can use large ceramic powders in order to achieve that, and the surface can be rough because that helps with a specific application. And I mean, you can read this. I don't need to read aloud all these comments, but you can see that depending on the application, you have specific requirements or desires in terms of dimensions of the part, in terms of the wall thickness of the part, in terms of the microstructure, dense or porous, for the solid component. And you're using ceramic powders that are fine or coarse, and you have different requirements in terms of surface quality. So the next step is to match these requirements with the technology that you're going to use for making these parts. And if you remember what I discussed this morning, then you will be able also to reach the same conclusion. So depending on the type of part that you want to make, these are the best technologies at the moment for making that part. So let me finalize this introductory lecture by making a few more general comments. So you need to be aware that additive manufacturing is not devised for simply substituting subtractive and formative technologies, but it is best for complementing them. So the message here is that if you are an industrialist or if you are a researcher, you do not need to immediately think that, oh, I want to make the part using additive manufacturing. You have to use additive manufacturing only when it makes sense in terms of shapes, in terms of properties, in terms of cost. So you need to definitely evaluate if it is advantageous to use additive manufacturing rather than conventional technologies. There is a wide range of components that it would not make sense to produce using additive manufacturing because it would be more expensive, because it could be slower, because the properties might not be as good as the properties of the conventionally obtained component. You have to be aware that not all ceramic systems have been validated yet for being produced using additive manufacturing, even though quite a few of the technology that I described this morning are actually, as I mentioned, materials agnostic, meaning that they can be applied successfully to any type of material because the material itself does not provide a limitation to the use of that technology. And in terms of industrialization, actual industrialization of these processes, there are now quite a few examples, not in the literature, but in the real world. Companies have started using additive manufacturing for making ceramic components. Later, I will mention which are the fields, in my opinion, that so far have been using additive manufacturing the most. Certainly, we need to be aware of challenges that you have when you want to use additive manufacturing. So if you want to make a dense body, meaning a body that has a certain structure, but basically it's dense, let's say I want to make something like this, then additive manufacturing is not really good because of the issues that I mentioned before in terms of wall thickness, in terms of final part density, and things like that. For instance, if you want to make fully dense monolithic ceramic bodies, you cannot use powder beds. If you have ceramic suspensions, that photopolymerization, you have limitations in wall thickness. With pastes, you can do that, but then you have a very strong stair-stepping effect. So you need to do post-processing if you need smooth surfaces. In terms of challenges, certainly debinding is the largest challenge for additive manufacturing. This is common also for other regular forming approaches, traditional forming approaches, but the content of organics in feedstocks for additive manufacturing is typically larger, posing stronger challenges. This I will discuss later. And the final message that I want to say is not just don't use additive manufacturing for making anything you can think of, but try to exploit additive manufacturing, of course, of ceramics in order to make it, to gain the most advantage out of it. And one reason for using additive manufacturing is to use it when it is more economical than conventional manufacturing. And this means that if the parts are complex, if the parts are small, if the parts are highly individualized, if you need to modify the shape of the part, the design of the part frequently, then additive manufacturing is certainly faster, more economical, and better than conventional approaches. So the applications where additive manufacturing works best is when parts are critical and expensive, where the tool costs are high in relation to part price, where the material costs are high in relation to production costs, because with additive manufacturing, you can optimize the amount of material that you use. You reduce the waste volume with respect to conventional processes. Certainly use additive manufacturing when the machining of the part is difficult. And as I mentioned, definitely use additive manufacturing if you need to modify the geometry of your part. In terms of applications, the additive manufacturing is most suited when you have to produce components that are based on the assembling of many parts, where the assembling of such parts costs are high. When you need more functionalities, let me just mention that now there is a new field in materials engineering, which deals with so-called architected ceramics or materials. And architected material is a component where the properties are not given just by the intrinsic characteristics of the material, like melting point, refractoriness, hardness, mechanical strength, and etc. But the properties are given by the structure, the 3D structure. And this relates mainly to highly or porous components. And so this new field of materials engineering uses structure as a way of guiding the properties of a component. And this is exciting because you can do computation, and you can use the computer to predict and optimize shapes, and you can produce those shapes using additive manufacturing. So this is quite unique. Additive manufacturing ceramics makes sense when more functionalities are required, especially when some of the functionalities are provided by the structure, not by the material. You can obtain easily lightweight structures. So think of filters, think of sandwich panels, cores, and think of very intricate structures that can be built using the technologies that I described. Additive manufacturing in ceramics should be used when higher efficiency can be realized within the entire value chain, including shipping, and for generating new, unique customer opportunities. A lot of customers are not aware of the potentialities of additive manufacturing, and you need to show them parts in order to trigger their imagination and link that to new business opportunities. There is certainly a future in terms of additive manufacturing of ceramics. I think we still need to develop further technologies. Hybridization is a possibility. For each technology that I described, I also mentioned some of the issues that people have with these technologies, or that these technologies intrinsically have. So there is the possibility of still working there. Ideally, people are looking for higher resolution, finer details, because this leads, for instance, to better surface quality. Large-scale printing is desirable, also from an industrial point of view, not just from the scientific point of view. Certainly, fast printing is important. If you look at the literature, CLIP is this technology for VAT photopolymerization that allows for continuous printing, speeding. And the advantage of continuous printing is that a good part of the time that it takes to print a part is related to the fact that you need to, once you inscribe the part with light, then you lift it, and then you fill the gap with a new feedstock that needs to be photopolymerized. So lifting and filling the gap takes time. So if you can avoid that, you can do this continuously, then you have a strong advantage in terms of printing time. And this has been demonstrated, and there's a company in California that does that very successfully for polymeric parts. I have not seen anything like that done for ceramics yet. For volumetric additive manufacturing, again, you don't have to build a layer each time you irradiate, so it's much faster technology. There are also other advantages that I will mention later on. For not just fast printing, but also for mass printing, people have experimented and proposed roll-to-roll 3D printing. So you have the possibility of generating a large volume of parts by using this type of technology that allows you to create parts quite fast. Multi-material printing is certainly an area of great interest because, of course, a lot of components are based not just on one material. And when I say multi-material printing, it could also be metal ceramic, and not just ceramic material. And then, of course, you have all the issues in terms of differential shrinkage and co-firing, all these things. But this is a lot of, and residual stresses, but this is a very interesting and promising field. Industrialization is a challenge in terms not just of the cost of the industrial printers, but in terms of the fact that, as I mentioned, if you need to have a large output, the only way is to have several printers working in parallel. So you need to create a printer farm, and it can be automatized with a robotic arm taking the part and feeding the system. There are some examples already from this point of view, but this has to be taken into consideration. But commercially speaking, now VAT photopolymerization can work with VATs that have this size, and people can print 1,000 parts, small parts, of course, using the same simultaneously. And this, of course, reduces the cost of the final. In terms of the future, I mentioned that you need to be able to select the best additive manufacturing technology for the production of a specific component. And this is ideal, but it is, I understand the issues from the point of view on industrialization, but I think this is a key way of really making sure that you can exploit the benefits of additive manufacturing of ceramics. And then the last point is DFAM, design for additive manufacturing. You need to think in a different way. You need to design the components using topological optimization. There are some commercially available softwares that do a great job, because you can, of course, couple the design with finite element analysis, for instance. So you can have the optimization simultaneously, for instance, of strength and permeability. And you can embed also an analysis of the tortuosity of the flow channels in order to optimize, for instance, the making chemical reactors or filters. So that's a very interesting topic. And if you are if you are a mechanical engineer, this is, then you are capable of doing this type of think of this type of developments. As a materials engineer, I'm not smart enough to be able to do that, but as a mechanical engineer, you certainly have the training that allows you to do that. So in conclusion, I would say that certainly additive manufacturing of ceramics is different from traditional forming, so molding, machining, casting. It changes the understanding of cost drivers and the time impacts and possibilities. It modifies the reality for the design, the manufacturing process, and conventional wisdom. But the engineers need to rethink and learn new ways to design. They need to consider the entire process chain to realize its full value. They need to think of the additional benefits for our customers and use additive manufacturing when these advantages are higher than the cost of production. So you should not underestimate the real potential of additive manufacturing, and you shouldn't limit it to traditional thinking of traditional objects and expecting the same output. You really have to try to think of new concepts in terms of shapes, in terms of properties of the overall part. So this this slide concludes my introductory talk, and then this series of lectures will continue with first discussing why it makes sense to use as an alternative to powders systems, precursors for ceramics that are not based on powders. Then I will discuss some characteristics of ceramic parts that are made using preceramic polymers. And then I will discuss additive manufacturing using preceramic polymers. Then we'll progress looking at other precursors. So I mentioned that ceramics are traditionally made starting from powders. And this certainly makes sense, and this shouldn't be substituted with anything else. But if you think of additive manufacturing and you think of using powder-based feedstocks, then you need to realize that there are some issues with that approach. And I already discussed this, but let me point out again these difficulties. So if you're using fine ceramic powders, and you're using VAT photopolymerization technologies, then using fine powders will lead to a very high viscosity. You need to use ideally special equipment, which is not cheap. And in any case, you're limited in the amount of powders that you can use physically. And then I mentioned that the stabilization of fine ceramic powders in the slurry is not that easy. And you have issues in terms of the type of material that you can produce. These days, some of these issues have been solved using high-intensity light sources, light engines, but you still have issues, for instance, in terms of penetration depth. So the layers are typically quite thin for parts made of silicon carbide, and this means that you have very long processing times. If you're using extrusion-based technologies, and I'm thinking especially of direct inviting, but this is also applicable to filament, fused filament fabrication, you have issues in terms of the surface quality, feature size, and resolution, besides having issues with the clogging of the nozzle. So if you use a fully liquid feedstock, and I'm sure you're aware of the fact that you can use chemical precursors for making ceramics, and these chemical precursors can be dissolved or liquid from the start. And if you use a liquid system, then you can exploit the more advanced stage of development for additive manufacturing technologies that have been applied to polymers. Typically, you can densify lower temperatures, and you can get stronger, more reliable green parts. In certain, for certain types of materials, you can obtain very specific features. For instance, we are working with a company for making glass, and we need transparent glass. And if you try to sinter glass particles to full transparency, that's not possible, because glass particles have a surface composition which is different from the composition inside the particle due to interaction with the environment. So even if you sinter to full density, meaning 99.99%, you still don't get a fully transparent part because of these so-called ghost interfaces. But if you start from a liquid precursors, then you can get transparent glass. Of course, if you're using liquid feedstocks, then you cannot use binder jetting, because you don't have, you cannot spread a liquid efficiently. You cannot use fused filament fabrication because you don't have a filament, and so forth. So the use of liquid feedstocks can give you some special benefits, but it's not generally applicable to all technologies, additive manufacturing technology for ceramics. Another point or issue for the use of liquid feedstocks is that I will be talking about three different families of feedstocks. One is preceramic polymers, the other one is solid gel materials, and the third one is geopolymers. I will talk about those very soon. But especially for polymer-derived ceramics, you have limitations in terms of the compositions that you can obtain. If you don't want silicon, then it's very difficult to use preceramic polymers, because there is only a polymer for boron nitride that can be used, which is borazine. So if you want to make titanium carbide, you cannot make it from a polymer, because there is no titanium-based polymeric material available, or I don't even know if you could make one. Fortunately, you can use solid gel-based formulations. I will give you examples of some research we had carried out for making different carbide materials and glasses. But the solid gel formulations are quite tricky to be employed for additive manufacturing. So I will now proceed to discuss the use of preceramic polymers. So I need to first tell you what preceramic polymers are. I will talk about making advanced ceramics from preceramic polymers, and I will not discuss in this lecture the use of additive manufacturing technologies for shaping preceramic polymers, because that will be the topic of the next two lectures. So here I'm simply telling you what preceramic polymers are, why it makes sense to use them. So first of all, the preceramic polymers are an early European achievement, especially in Germany by Fritz and Rabe, Engel and Herbert. But there was a research center outside Oxford called Harwell Laboratories, where two researchers from England, Chantrell and Popper, started discussing using polymeric materials for making ceramics, and they published something already in 1965, and then other work came after that. The most famous work is the one by Yajima, of course. So Japanese scientist working for Nippon Carbon Company, and he developed a precursor for silicon carbide, which is of course a very, very significant ceramic material for a wide range of high-end applications. And the main point of Yajima's work was to develop ceramic fibers. Before him, there were no ceramic fibers, I mean, besides glass fibers. But glass fibers have, of course, high temperature limitations. You cannot use them above the glass transition temperature. So this development was extremely important. And today, all the high-end ceramic fibers used, for instance, in ceramic matrix composites, and of course, you want the fibers to provide toughness to your brittle ceramic material, are made using preceramic polymers for silicon-containing materials, like silicon carbide. For oxides, like mullite, people use salt gel approaches. 3M has developed some oxide-based fibers using salt gel. And you can see there some other developments from the point of view of the history of the material. If you are really, really interested in polymer ceramics, you can buy a book that's been translated also into Chinese, or you can read some review papers that might help you in understanding more about preceramic polymers. So what are preceramic polymers? They are actual polymers that contain silicon atoms in the backbone. Everybody's familiar certainly with siloxanes, polysiloxanes, which are conventional polymers from the point of view of the molecular structure or the architecture. They contain silicon and oxygen atoms in the backbone. But there are also other types of polymers that still contain silicon, such as carboxylanes and siloxanes, that will give you a ceramic material. All these polymers will give you a ceramic material after a so-called ceramization step. So you make your part you shape your part using these polymers. You obtain a fully polymeric material that has the characteristics of a polymer, and then you convert that to a ceramic material by the elimination of the organic moieties. So you can do that through typically thermally, and if you want to retain carbon in the material, then you need to do that in inert atmosphere. Or if you want to obtain oxides, then you can process into in air. And let me also mention that you can also strip or destroy the organic moieties. And once you do that, you obtain a fully ceramic material, also using ion irradiation. But this works well with coatings only, because you selectively strip hydrogen from the organic moieties and you transform that material into a fully inorganic material. Let me mention that when you're using preceramic polymers, you have a lot of advantages in terms of shaping, forming. You can use any type of technology that you apply to polymeric materials and to shape your component, and therefore you can blow them. You can make hollow components, porous components. You can spin them into fibers, solution spinning or melt spinning. You can extrude them. You can do injection molding. Anything you can do with a polymer, you can do with a preceramic polymer, with the advantage that after shaping, then you can transform that into ceramic. Of course, you can also, at the same time, add other fillers to the material that will become part of the final ceramic, but I will be talking about that a little bit later. Why are we interested in preceramic polymers? Well, preceramic polymers will give you, even if you're not adding any fillers, they will give you materials based on either silicon carbide, silicon carbonitride, or silicon oxycarbide. And especially the last two materials have some interesting and unique properties due to the microstructure at the nanoscale. The polymer-derived ceramics contain excess carbon. People say graphene or graphene-like layers, basically turbostratic carbon disorder graphite structures in the material and at the nanoscale. And this gives the material very interesting properties, for instance, high viscosity, high microstructural stability. These carbon nanoclusters give you luminescence, for instance, or electronic conduction. One of the main fields of applications of preceramic polymers is electromagnetic wave absorption. And there's a lot of work coming out, especially from China, on using polymer-derived ceramic parts that you shape using additive manufacturing, and you use the shape to control the absorption, the reflection of the waves and the penetration of the electromagnetic waves into the body, and you use the composition of the material to absorb the electromagnetic waves. So this gives you a distinct advantage with respect to other materials. Let me mention that, point out what I mean by high microstructural stability. There was a paper by Professor Ralph Riedel was published in Nature in the early 90s, where he demonstrated that if you have a polymer that contains silicon, carbon, nitrogen, and boron, so a so-called polyborosilicene, then you obtain, after processing through pyrolysis at 1,000 degrees to 100 degrees, you obtain silicon, nitrogen, carbon, boron material, and that is amorphous. And it crystallizes above 2,000 degrees. And if you're familiar with ceramic fibers, you know that one of the main limitations of the use of ceramic fibers is the loss of strength due to grain growth. So if you have a crystalline fiber, then above 1,600, 1,700, the strength goes from 3 gigapascal tensile strength to few pascals. And that's not good. But if you can keep the microstructure amorphous to high temperature, then you retain the strength. So that's quite unique and very important. And another thing that makes sense to comment on is that high viscosity, meaning, and I will tell you about the microstructure of polymer-derived ceramics. I mentioned that they are amorphous. There's a discussion if they are actually glasses. There's a distinction between amorphous material and a glass material. A glass material forms typically by the solidification of a liquid, and it has the glass transition temperature, meaning that above a certain temperature, you cannot use it because it starts flowing. And if you have a high viscosity in your molten phase, you can use that material at a much higher temperature. And polymer-derived ceramics have been used, for instance, to generate highly viscous phases at the grain boundary of, for instance, silicon nitride and silicon carbide. So the creep resistance of materials produced using an addition of preceramic polymers can operate a much larger temperature with respect to conventional. So the polymer route to nano structural ceramics, it follows this pathway. You start from the molecular precursor, and you can recognize that this is quite an interdisciplinary field, because you start from molecular precursor, and if you're a polymer chemist, then you can generate polymers with different characteristics. And these characteristics of the molecular architecture will affect the shaping, the cross-linking of the material, so the processing of the material, and then you obtain your polymeric material that you convert to a ceramic through pyrolysis. And you need all these expertise, is useful to understand and control the process. There are a lot of parameters in this process, but you can tailor the microstructure and the composition and the properties of the final material using this approach. So in terms of the types of preceramic polymers, there are some features that you can use to modify and design the preceramic compound at the molecular level. So you can see here typical backbone or molecular structure, not structure, molecular formula for your preceramic polymer. So you have silicon atom in the backbone, and you have some side groups, and you have also some groups attached to silicon that constitute the polymeric backbone. So if you change X, the backbone, then you have different classes of silicon-based polymers. You have silanes, carbosilanes, siloxanes, siloxanes, or you can have imides. And if you modify the functional groups R1, R1, and R2, then you modify the final composition of the material, the carbon content of the final material, which affects properties such as oxidation resistance, but also functional properties such as electrical conductivity, electromagnetic wave absorption. And by modifying those two components, you can modify the chemical and thermal stability of the material, as well as the rheology. So this is the types of preceramic polymers that you can use. They all are based on silicon. As I mentioned, you can also have borazine, which is a boron nitrogen-based material, but it is quite specialized, and not many people use that, and there is no commercially available polymer based on that. So some of these are commercially available, other ones are synthesized in the laboratory. And in order to compete with traditional ceramics, you need to be cheaper, or you need to afford better properties or unusual properties. And it is this latter possibility that is mostly exploited with preceramic polymers. So you need to fulfill several requirements in order to obtain suitable preceramic polymers. You need to have a sufficiently high molecular weight, because what happens is that, as I mentioned, you get your polymeric body, and then you transform that into a ceramic through thermal treatment, pyrolysis process. And if your molecular weight is not high enough, you have a lot of components that are eliminated during pyrolysis, volatile components that are eliminated during pyrolysis, and this leads to a low, what is called ceramic yield. You need to have suitable rheological properties and solubility for the shaping processes. So from the synthesis of your raw materials, you can either obtain a liquid or you can obtain a solid. And one very important point is that once you obtain, you make your preceramic polymer, you shape it, you obtain your ceramic, your preceramic component, you pyrolyze it, you obtain your ceramic part. But of course, you're familiar with thermoplastic polymers, and you know that when you heat a thermoplastic polymer, it starts flowing. So if you shape a thermoplastic polymer and then you heat it up, it loses its shape. So in order to avoid that, you need to embed into the preceramic polymer the possibility of cross-linking. So you need to use something that can be shaped as a thermoplastic polymer, but is able to behave like a thermoset polymer during pyrolysis. And not all commercially available materials, siloxanes, or preceramic polymers have this possibility. For instance, Yajima's polycarbosilane cannot cross-link, so you can make very nice fibers, but then if you try to pyrolyze them, they melt or they soften. And so what you do is that you need to, for instance, they used to oxidize, they used to heat treat the polymer fibers in an oxygen atmosphere in order to generate silicon-oxygen-silicon cross-linking bonds and obtain a material that was not pure silicon carbide, but a material that was stable in pyrolysis. In order to avoid that, you need to use, for instance, electrobeam curing or gamma irradiation curing, which is, of course, more difficult and more expensive. So it's important to be able to lose the shape that you have given to the polymer. And one important point is that not all polymers that contain silicon can be considered a preceramic polymer, in the sense that there are some commercially available siloxanes, for instance, that pretty much completely volatilize during pyrolysis. And this is due to the molecular architecture that they have. So in order to avoid a lot of losses, you need to avoid using preceramic polymers that have a linear chain, because a linear chain during pyrolysis will break down into shorter chains, which tend to evaporate. So you will start from 100 grams of your shaped polymer, and after pyrolysis, you will end up with 7 grams or 5 grams of your ceramic material. So it doesn't make sense to volatilize 93% or 95% of your material. And to avoid that, you need to build a specific molecular architecture of your preceramic polymer. This is an example for silicones, actually silsesquioxanes. So silicones that have specific type of nonlinear structures that is the key to what we call a high ceramic yield. Let me mention some of the technologies that have been demonstrated for making parts using preceramic polymers. Additive manufacturing is not here because when I prepared this slide, the field was not yet developed. So of course you can cast, you can injection mold, you can do tape casting, you can foam, you can press, you can use preceramic polymer to impregnate, to close porosity in a ceramic body. So that's very useful. You can make coatings, you can extrude, you can make fibers. Oh, actually additive manufacturing, I added it there, yes. You can do blank machining. So one of the advantages of having a polymeric part is that you can machine it before pyrolysis. So you can obtain parts that have interesting shapes in this way with all the defects of subtractive or limitation of subtractive technologies. And one interesting possibility is that you can use preceramic polymers for joining. So you use that as an interlayer between ceramic blocks, and after pyrolysis, you have developed a ceramic bond. By the way, we also used microfluidics for making specific parts, electrospinning, electrospraying, and you can also use the vapor liquid solid formation on nanowires. I will show you some examples. During pyrolysis, you can catalyze the decomposition of the material specifically to form nanowires. And that's quite interesting for certain applications. You can also do emulsion processing, and you can do nanocasting. You have to be aware that besides cross-linking, so after shaping you need to cross-link, otherwise you will lose your shape. I didn't mention, but some of these polymers, especially silanes and carbosilanes, are moisture sensitive. So rather than air, I would say moisture reactivity is an issue. So if you want to get oxygen-free ceramic, you need to avoid processing in the normal environment. You need to use a glove box. Let me simply add one point. If you remember, I mentioned that you can process a preceramic polymer body using mixing to the preceramic polymer some fillers, some particles, and if the particles are enough beyond a certain threshold in terms of their volume within the body, then they would form a self-sustained structure that avoids the melting of the material. So if you have a highly filled system, you can pyrolyze without losing its shape, the shape of the part, without cross-linking. Cross-linking is, so these are the different techniques that have been applied so far without fillers, and cross-linking must occur during or after shaping, and certainly before pyrolysis. In terms of cross-linking, you can use siloxanes that contain silanols. There are polymers that have SiH and vinyl bonds, SiH moieties and vinyl moieties. So you can do this type of reaction, or you can have some other reactions like the alcoholysis. If you're processing, typically you want a rather high molecular weight in your material, and this leads to working with a material that is solid, that is a thermosetting material with the possibility of, a thermoplastic material with the possibility of becoming or behaving like a thermoset at higher temperatures, and or after post-processing, and which means that during processing your material, during shaping your material, you have the melting of the material, and depending on the type of polymer, the molecular weight and the molecular architecture, you can have different viscosity values that are best for different technologies, such as tape casting, extrusion, injection molding, or pelletizing. I mentioned that you want to transform, or you need to transform your polymer to a ceramic material. I will discuss what happens shortly. But in terms of the methods, you can use conventional oven pyrolysis, typically in a tube furnace with a flowing gas. You can use a pressurized system. You can use microwave pyrolysis, and you can use warm pressing. It's written hot, but it is actually warm pressing, so 150 degrees, for instance. Ion irradiation works only for coatings. You can use all these technologies here. including chemical vapor deposition. High pressure diamond anvil cell has been used, and this is quite interesting because it gives you a specific crystalline phases. Laser pyrolysis can be used, especially for coating. So you can inscribe a preceramic polymer-based coating using a laser, and you transform in situ the material to a ceramic part. You cannot do that in bulk, but on coatings works quite well. And actually, if you want to retain carbon into the system, as I mentioned, you need to use inert atmosphere. But if you use laser pyrolysis, you can do that in the open environment, because the decomposition and forming of ceramic bonds, the composition of the polymer forming of ceramic bonds is so fast that the material does not oxidize. So this is quite useful. Of course, you can use also a reactive atmosphere. For instance, people have been processing in ammonia in order to embed a large amount of nitrogen in the system. And during pyrolysis, you can control the heating rate, the heating temperature, the dwelling time, and this leads, all these features will lead to control of the composition of the so-called ceramic yield, the crystallinity, the properties of the material, therefore affecting the properties of the part and the applications of the part. So let me mention something about the so-called polymer to ceramic transformation. So I told you that you need to pyrolyze in inert atmosphere or in air if you want to get an oxide material, your shaped part, and the shaped part undergoes the decomposition of the polymer and its transformation into a ceramic material. And if you look here, you can see that you have this transformation occurs with the destruction of the organic moieties that leads to weight loss. So the so-called ceramic yield has been defined as the amount of ceramic material that you get out of a pyrolysis process of your preceramic polymer. And ideally, you want it to be as high as possible. You want to start from a shaped component, 100 grams of your part. You want to end up with the same amount of ceramic. But this is very difficult to achieve. You can control the ceramic yield by controlling the molecular architecture of your preceramic polymer. And in order to make sense, the ceramic yield, from any point of view, the ceramic yield needs to be higher than, say, 50 weight percent. The best preceramic polymers have a ceramic yield between 75 and 90 weight percent, which is quite high. The bad preceramic polymers, like commercially available UV curable siloxane, they have been developed for conformal coating of electronics, for instance. They have linear chains, and the molecule and the weight loss is very high because they have not been designed to withstand high temperatures. So in that case, the ceramic yield is as low as 5%. All the rest is eliminated. So you want a high ceramic yield, and the material goes to shaping, often thermal, using temperature. Then you have cross-linking, typically below 400 degrees, and then you have the polymer to ceramic transformation within the typically 400 to 700, 800 degrees. And during this process, you are eliminating all the organic moieties. You are decomposing, not eliminating. Decomposing the organic moieties, and carbon stays there, at least in part, while you're releasing molecules such as methane, benzene, and other species. And then if you increase the temperature further, then you might have crystallization of your material. And let me point out the fact that during the polymer to ceramic conversion temperature range, so between 400 to 800 degrees, you have this change in properties from polymeric material to a ceramic material. So if you want a ceramic, you need to process above 800 degrees. If you want a polymer, you need to stay with, in terms of behavior, you need to stay below 400 degrees. This intermediate stage has been exploited for making specific components that have some specific applications. But in that case, you have a material that is not yet a ceramic and is not fully a polymer in terms of behavior and composition, because you have not eliminated all the organic moieties. So you can see that from different preceramic polymers, you obtain different final ceramic materials, and you can have different compositions that, and the variability, especially, you should also here have SIXCY, because the variability in composition is related to the amount of carbon that you have left in the material or nitrogen. And it is very, very difficult to obtain pure silicon carbide with no excess carbon. In terms of the on the weight loss, this is misplaced, because this is the properties, the stability of the material to higher temperatures, so not during the polymer to ceramic conversion, so I can skip that. But here you can see, depending on the type of preceramic polymers, these are all different preceramic polymers, you can see that different organic molecules are generated during processing. And of course, what changes is not just the composition of the gas that you are releasing, but also the volume of the gas that you are releasing. So all these transformations, all this gas release occurs with shrinkage and weight loss. And you have to make sure that you do not generate cracks during pyrolysis due to these stresses related to the release of gas. Here you can see, for instance, in silicones, how by modifying the type of polymer that you're using, you can modify the content of or the ratio between carbon and silicon in the material, so the content of carbon in the material. And this is quite useful because carbon is an active component in your final ceramic from the point of view, for instance, of optical properties such as luminescence or conductive properties or electromagnetic wave absorption properties. So it's very good to be able to tailor the carbon content in your material. And this is specifically for silicones. I didn't mention that if you want to make a silicon carbon oxygen material, there's no other way than using preceramic polymer. If you try to do that starting from silicon carbide powder and silica powder, you are not able to obtain a silicon oxycarbide material because it's not thermodynamically stable. So there are a lot of parameters that play an important role in the processing of preceramic polymers. And this applies to any type of technology that you use for shaping. And this also, of course, is related to the use of additive manufacturing. So the characteristic of the precursors, the presence of fillers, I will mention something later, the shape of the fillers, dimension of the fillers, the type of atmosphere, the atmospheric pressure, heating rate, heating temperature, dwelling time. And we can skip this. This is just to show that in after pyrolysis of any of the preceramic polymer classes, so siloxanes, silazanes, carboxylanes, you have residual carbon. For instance, silicon oxycarbide is black, not because it is intrinsically black, but because you have so-called free carbon. So you have graphene type turbostratic carbon sheets that give you a black color to the material. And this is the Raman spectrum of different materials. And you can see that by modifying the pyrolysis temperature, you modify the order of your turbostratic carbon, and you start graphitizing the carbon, therefore modifying the properties. At the nanoscale, these materials, depending on the pyrolysis temperature, they are either fully amorphous or they have free carbon clusters. And often for the temperature regions where we typically process these materials, so below 1400 degrees, carbon is disordered, so you have turbostratic carbon. So turbostratic carbon is like graphite carbon layers, but each layer is oriented in a non-ordered fashion. So it's a disordered layered carbon. And again, people talk about graphene simply because it's fashionable, but you do not have individual sheets or exfoliated sheets of carbon inside these materials. And you can see here that for silicon oxycarbide, 1000 degrees, you have a fully amorphous material. If you start heating at higher temperatures, then you have carbothermal reduction reactions. So you expel CO2 and you form silicon carbide. And depending on where you stop the process, you have a structure that is based on a nanostructure features, a microstructure that is based on nanostructure features. You have silicon carbide nanoclusters. You have regions where you have silica-rich material, and you have some continuous turbostratic carbon pathways depending on the content of free carbon. And if you have a continuous pathway for carbon species, then of course you have conductivity or semiconductivity. You can model what the carbon does, where the carbon goes, so you can see that depending on the composition and pyrolysis temperature, these are calculations for different materials. You can see that you can generate these structures inside your ceramic material. And by the way, silicon oxycarbide materials have been used to propose for embedding lithium ions inside the turbostratic carbon, and they are being used quite effectively for making battery anodes. So you can modify preceramic polymers, and there have been examples in the literature and also in industry. And if you have, for instance, a polymer like this, you can add atoms that are not there by chemically reacting with other materials, for instance, alkoxides, and you can make, therefore, single source precursors that are still that you can still process using the technologies that I mentioned briefly before, and obtain, in the end, nanocomposites that have interesting properties. I mentioned that you can use fillers, and fillers are simply particles that you can add to your ceramic material to modify the properties. And if you do that, you end up with a composite material based on your matrix deriving from the preceramic polymer and the particles that you have embedded. So there's one interesting point to make, is that if you use what is called a passive filter, for instance, a carbide or nitride filler like silicon nitride powder, you do pyrolysis, nothing happens to the silicon carbide or silicon nitride. So you can exploit, silicon carbide to provide certain property to your material in the end. But you can also add what is called active fillers. And these are called active fillers because they react either with the preceramic polymer itself or more often with the decomposition products of the preceramic polymer. And Professor Peter Geil from Erlangen University is the one that started this branch of the field. And he realized that if you add metallic particles to your preceramic polymer, during pyrolysis, these metallic particles will convert to carbides. You're pyrolyzing in inert atmosphere. And this is quite interesting and useful. One of the reasons why this is useful is that you not only generate useful phases like metal carbides, but that affects also the shrinkage in your material, as I will explain in a moment. One difficulty with this approach is that typically you get not only metal carbides, but you can also, at the same time, you obtain silicides. So if you want phase pure material, it's a little bit complicated. If you use oxide particles or oxide precursor particles, calcium carbonate, for instance, then you can convert everything into a fully oxide ceramic. For instance, we make wollastonite, which is a calcium silicate, which is bioceramic, by simply adding calcium carbonate to the preceramic polymer and firing in air. So this is what happens if you use your preceramic polymer. After pyrolysis, you either obtain a cracked component due to the release of gas during the decomposition. And this is, of course, related to the volume of the part that you have produced. This doesn't happen, for instance, in fibers or coatings, but it happens with larger bodies. And in any case, after the conversion, you have a large volume shrinkage. Typically, the linear shrinkage is of the order of 30 to 40 linear percent, so it's quite substantial. If you add the fillers, if they are inert or passive, they reduce the shrinkage because you are eliminating volume of the material that is shrinking, but you still get some cracks. But if you use an active filler, what happens is that, as I mentioned, you have the conversion to carbide. And if you look at the density of the carbide with respect to the density of the metal, it is typically 2 to 3 times lower. So basically what you're doing is that you're forming a new ceramic phase that occupies a larger volume. So in this way, you can reduce the shrinkage quite effectively and end up with a material that is fully ceramic. So you can see that if you do sintering or particle-based materials, you have a certain sintering shrinkage. If you do, if you use no fillers, then you have your shrinkage and you end up with porosity and cracks. If you use active fillers, you can even reach a larger volume during pyrolysis and generate near net shape components. So there has been quite a lot of interest in using preceramic polymers mixed with metal particles for different applications. When I say fillers, of course, I mentioned particles, but you can add viscose, platelets, short fibers, nanotubes, and so forth. So you can use the fillers to control the shrinkage, but also to control the properties. And this is what happens when you synthesize a silicate material from silicones and fillers. And depending on the temperature at which you fire the material, you can obtain amorphous or you can obtain a crystalline material. So the purpose of what I'm saying now is to give you an overview of what preceramic polymers are, what are the advantages, and then we will transfer this knowledge to discussing additive manufacturing of preceramic polymers to make components with specific properties. We will be mainly talking about shaping, not about finalized parts, because I don't have time. But this is the reason why I'm spending some time for discussing preceramic polymers.
So in terms of the challenges related to additive manufacturing of ceramics. One of the points that you had put up in your slide is multi-material printing. So what is your experience with multi-material printing, and what kind of difficulties did you expect, and how do you think this can be resolved eventually? Because I think it's not like metal printing where things are easy. In
Yes.
ceramics, it becomes more complicated.
So I would say that you have you need to look at two different issues. One is the shaping, the other one is the processing, sintering, okay? So in terms of shaping, you need to use a technology that allows you to deposit two materials sequentially, okay? And so far, for instance, for VAT photopolymerization technologies, until maybe 3 years ago, there was no known equipment that would allow it to do that. Now, if you go to China, they have been developing VATs that, for instance, are circular. They are divided into a certain number of parts, and you're building your part here, and then the VAT rotates. So you make one layer, then you have to lift anyway because you need to fill the gap with the material. So if you want the same materials and another layer of the same material, leave it there. If you want another material, the VAT rotates and then you dip it again. It's not that simple. I mean, rotating is simple, but it's not that simple because you want typically clean interfaces. So there needs to be a way of, let's say, cleaning the bottom of the part that you have just formed from the residues of the previous material. So that's where the challenge lies. Other possibilities are using a printing head that moves. You have a certain number of VATs, and the printing head moves between these, and the commercial machine has only two materials. We just purchased one. We haven't used it. And after printing, you need to clean the surface. So that's very slow. For extrusion, you have certainly multi-material, filament possibilities, and often this is used simply to one filament is the material that you want, the other filament is a sacrificial material that helps you sustain the part that maybe is inclined in shape, but it could be also a material that is non-sacrificial. So that has been exploited. And for instance, IKTS in Dresden, they have developed this melt extrusion based on pellets, and you simply have different extruders with different pellets, and you can make multi-material. So in terms of shaping, apart from VAT photopolymerization, which is still a challenge, but there are commercially available examples, you can do it. Then the issue is you need to sinter. And the problem is that, okay, you say, for instance, with the filaments, one material shrinks, the other material shrinks. So basically, you should be okay. But in terms of how the material shrinks, it's not the same because the polymers often are not the same that you're using for different compositions. So the post-shaping process is the real issue. Of course, you can exploit, for instance, the use of ceramics with different coefficient of thermal expansion. So if you couple mullite and zirconia, for instance, or alumina and mullite, then you can make parts that are, for instance, based on multi-layers. And if you can exploit the fact that one part shrinks more with heat after forming, and then you can develop compressive stresses at the surface of the part. So for instance, if you put alumina outside and mullite inside after processing, no, actually the opposite. So you put mullite on the outside, alumina inside. When you use the part, the alumina when you cool down the part after sintering, alumina shrinks more than mullite, and therefore mullite goes into compression. And if it is on the outside, then you have embedded beneficial stresses. But sintering is certainly a major problem.
Sir, I have one just kind of get insights from you on, like, for ceramic processing, the green density forms a critical aspects. So through 3D printing process, like even by binder jetting or by polymerization method, what could be the suggestion if you wanted to have a higher initial green density?
So if you want a high green density, you can use any additive manufacturing technology, but binder jetting.
Right.
Binder jetting is not capable of providing full density, high density green body.
Okay.
But if you look at the density of the solid part of a component printing using direct inviting or VAT polymerization technologies, the density there can be high.
Can be higher. Okay.
Yeah, that's for the density of the produced as prepared part. Then you have to transform it into ceramic, and if you are using VAT photopolymerization, then the content of ceramic particles in the system is not very high, and therefore you have large shrinkage, but you can still sinter to full density.
So one more, adding on to the same thing, it is playing with the process parameter or the ceramic loading in the, or both the way together.
So I would distinguish between obtaining a dense green part and obtaining a dense sintered part. So for obtaining a dense green part, you can achieve that, as I said, with any technology besides binder jetting. To obtain a dense sintered part, then you can achieve that with any additive manufacturing technology but binder jetting, because of the starting of a large with a large porosity that prevents you from sintering to full density. Simply, if you have a part that has been produced by VAT photopolymerization and you want full density, the shrinkage will be much higher than if you start from a part that has been produced by direct inviting.
So when you are using metals for active fillers, so the reaction between the metal and the maybe carbon, if it is forming carbide, how the volume difference comes into play, like whether it leaves a porosity or.
So this has been well explained in the paper, I think in 1995 by Peter Greil on active filler processing of preceramic polymers. For each carbide, you have a different density, and therefore you have a different volume change. So you can compute how much volume change you would have depending on, in the entire part, depending on the content of particles and type of particles. Assuming, I mean, things get difficult because you have to assume that you get stoichiometric carbides, which is not always the case. You should assume that you don't have side reactions, which is not the case because you have the formation of silicides. So the actual volume change is difficult to predict because all these changes in the phase assemblage during pyrolysis. But there have been attempts to show what happens.
Unlike metal additive manufacturing, ceramic additive manufacturing is still at the, although we have commercial companies and so on, still I think people are trying to understand many aspects of additive manufacturing, including defects and so on. And again, ceramics being brittle, flaws in materials in ceramics can be very detrimental.
Yeah.
So is there any, I don't know if somebody asked this question already, after you you make the green body. Is there any other way, particularly a green body with complex shape? Is there a way to actually increase the green density? I'm not sure. Somebody asked me that. Asked
Yes.
that question.
So I mean, so the green density of the body, meaning the density of the solid part constituting your component, is high for all additive manufacturing technologies apart from binder jetting. So you get a dense part from butt photopolymerization, a dense solid, you get a dense solid when extruding the material. Then the other issue is the density of the sintered part. And you can get fully dense parts from that photopolymerization and from direct inviting or extrusion technologies, not from binder jetting. But the difference between the two is that the VAT photopolymerization part has a much higher content of organics. So the shrinkage is higher and the possibility of having defects such as voids or cracks is much higher. And so you have much higher, stronger limitation in terms of the part thickness that you can successfully convert to a ceramic.
Where do you think in the next 5 years we will be in this?
Okay, so in terms of shaping technologies, in terms of additive manufacturing technologies, I think that we will see many more possibilities for multi-material printing. I'm not sure if people can invent additional ways of additively manufacturing shapes besides using these technologies. Hybrid technologies or printers have been developed, for instance, to combine the high precision that you can get with VAT photopolymerization technologies with a much larger printing window that you have with extrusion-based technologies. You can use a robotic arm. You can make a very large part with extrusion-based technologies.
So, do you feel the nozzle geometries can be optimized in case of FDM-based, extrusion-based methodology to get nice interlayer bondings in the green, like during the printing stage?
Can you reformulate the question?
Okay, so we can see more or less every FDM printers have a cylindrical nozzle.
Yes.
So do you think that we have to optimize the nozzle geometries?
Yes. So in terms of nozzle geometries, there are some examples in the literature. Some people have developed size adjusting nozzles, which is quite nice because it means that you extrude with this size and then you tell the nozzle to expand or contract, and then you change the size, okay? So that's one possibility. In terms of shapes, you can buy different shapes. So for the nozzles, I mean, you can develop your nozzles, for instance, using specialized metal shaping technologies. For instance, we have core shell nozzles. So if you're familiar with electrospinning, you know that you can have nozzles that can have up to 3 different materials. And you can use that type of concept for making, for extruding, for instance, we are extruding core shell ceramic materials using this approach. And this is still conical or cylindrical. But then you can have different shapes. You can have star shapes, you can have flat shapes, and I mean, you can develop your own commercially available, since there is a lot of work on spreading of adhesives, for instance. You can go on specialized suppliers and buy inclined nozzles that are shaped like this and so forth. For instance, if you work in templated ceramics, you could use extrusion. I didn't mention this, but I will show that in other lectures. If you have a high aspect ratio filler in your feedstock and you're extruding, so if you have, for instance, chopped fibers, when you extrude, what happens is that you align the high aspect ratio fillers along the direction of the extruded filament. And this means that if you work with templating ceramics, for instance, for piezoelectric ceramics to enhance the properties of the material, you can have some seeds for generating the crystal phases that you want, and you can stack them in a oriented fashion. So I will show you some examples, for instance, of ceramic matrix composites obtained from direct inviting, where you have chopped fibers that are aligned inside the filament.